Our universe is fine-tuned to a precision of 120 decimal places. Nobel Laureate Steven Weinberg at the University of Texas calculated this specific vacuum energy density. However, if this value changed by a hair, your brain would instantly vaporize into a void. Leonard Susskind realized that this terrifying precision destroyed Einstein's dream of a single. He argued that we live in a statistical accident, a 1 in a trillion outcome within a vast and chaotic cosmic landscape. The crisis began with a number called the Cosmological Constant, denoted by the Greek letter lambda. Back in 1917, Albert Einstein added this fudge factor to his equations of general relativity to keep the universe static, only to later abandon it as his biggest blunder when Edwin Hubble proved the universe was expanding. For decades, physicists assumed the value of this constant was exactly 0. But in 1987, the Nobel Laureate Steven Weinberg published a paper titled Anthropic Bound on the Cosmological Constant, where he made a radical and unsettling prediction. He argued that if the constant were even slightly larger than 0, its repulsive force would have pushed the early universe apart so violently that galaxies, stars, and planets could never have formed. Then came 1998. Two independent teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, observed distant exploding stars and realized that the expansion of the universe wasn't slowing down, it was accelerating. This meant dark energy was real, and the cosmological constant was not 0. It was measured at approximately 10 to the power of -122 in Planck units. To give you an idea of how absurd that is, imagine trying to balance a pencil on its graphite tip on a table that is shaking during an earthquake for 13 billion years. Standard particle physics predicted a value 120 orders of magnitude larger. This is the greatest discrepancy between theory and observation in the history of science, a fine-tuning problem so precise that it makes the probability of our universe existing feel like a mathematical impossibility. Susskind realized that the old way of doing physics, searching for one, we weren't looking at a master design, we were looking at a statistical freak accident. Back in the mid-1980s, there was this intoxicating sense of inevitability in the air. We thought we were just a few scribbles on a blackboard away from Einstein's dream, that single, crystalline equation that would explain every sun, every atom, and every heartbeat as the only possible way a universe could be. At the heart of this was string theory. Think of it like this. If you look closely enough at an electron or a photon, you won't find a little point-like dot. Instead, you will find a tiny, vibrating loop of string. It is like a cosmic guitar string. Pluck it one way, it vibrates at a certain frequency and looks like a gravity particle. Pluck it another way, with a bit more tension, and it looks like a piece of light. The music of these strings was supposed to be the symphony of the cosmos. It was elegant, it was beautiful, and for a moment, it felt like the ultimate victory of human reason. We really believed that the math would eventually point to one single unique solution. But mathematics has a way of being far more complex than our vanity prefers. For the math of string theory to hold together without collapsing into logical nonsense, it required the universe to have not 4 dimensions, but 10. Now, you look around and you see up, down, left, right, forward, and back. That's 3. Toss in time, and that's 4. We theorized they were compactified, curled up so tightly into microscopic shapes called Calabi-Yau manifolds that we simply could not see them. Imagine a garden hose stretched across a vast canyon. From a mile away, it looks like a one-dimensional line. But if you are an ant crawling on that hose, you realize there is a second dimension, the circle, going around the pipe. The problem, the one that started keeping us up at night, was that there is not just one way to curl up those extra 6 dimensions. There are countless ways. And this is where the theory of everything started to feel like a theory of anything. Every different way you fold those dimensions, every way you wrap magnetic-like fluxes around the holes in those shapes, changes the physics of the resulting universe. It changes the mass of the electron. It changes the strength of gravity. It changes the very vacuum energy of space itself. For years, physicists tried to find a reason why one specific folding was the right one. We looked for a principle that would say, this is the one, but the math refused to cooperate. In the year 2000, two physicists, Raphael Bousso from UC Berkeley and the late brilliant Joseph Polchinski from the Kavli Institute, published a paper titled The String Theory Landscape of Flux Vacua. They did something radical. They sat down to count the possibilities. They estimated there were something like 10 to the 500th power possible ways to configure these extra dimensions. To give you a sense of that number, there are only about 10 to the 80 power atoms in the entire observable universe. If you tried to write that number out, you would have a 1 followed by 500 zeros, a figure so vast it makes the word astronomical seem like an insult. This was not a unique solution. We had set out to find the one true path to the peak of the mountain, and instead, we found ourselves lost in a dizzying, nearly infinite landscape of possibilities, where every valley represented a different universe with its own laws of physics. We were no longer looking for a single elegant equation. We were looking at a statistical haystack. Everything we believed up to this point was wrong. We were not looking for a needle in a haystack. We were looking at the haystack itself and realizing that every straw was its own reality. By the year 2000, theoretical physics was staring into an abyss of its own making, and it took a few rebels to realize that the abyss was actually a map. At the Kavli Institute for Theoretical Physics in Santa Barbara, Raphael Bousso and Joseph Polchinski were wrestling with the math of D-branes and string vacua. They weren't looking for a multiverse. They were trying to solve the vacuum selection problem. The annoying fact that string theory wouldn't just give us one tidy set of laws. What they found, and published in their landmark paper, The String Theory Landscape of Flux Vacua, was a number that almost looked like a typo, 10 to the power of 500. That is a 1 followed by 500 zeros. To give you some perspective, there are only about 10 to the 80 atoms in the entire observable universe. This wasn't just a large number, it was a mathematical continent, a sprawling, chaotic geography of possibilities. Now you have to understand the mood in the community at the time. Most of my colleagues, the heavy hitters at Princeton and Harvard, they wanted a single, unique, beautiful equation, the kind you could fit on a t-shirt that would explain why the electron has the mass it does and why the cosmological constant is what it is. But when I saw Bousso and Polchinski's work, I realized the game had changed. I remember sitting at Stanford, looking at these numbers and thinking that the failure of string theory to give us a unique it was the answer. In 2003, I formally introduced this idea in a paper titled The Anthropic Landscape of String Theory. I argued that we had to stop looking for a perfect universe and start looking at the statistics of the landscape itself. Everything they believed up to this point was wrong. The search for a single, elegant solution was a wild goose chase, because our universe isn't a unique mathematical necessity. Think of the landscape like a vast, mountainous terrain, stretching out forever in every direction. Each valley in this landscape represents a different way that those extra 6 dimensions from string theory can be curled up or compactified. In one valley, the dimensions are twisted like a pretzel, giving rise to a universe where gravity is 10 times stronger than ours. In another valley, the fluxes are arranged such that atoms can't even form. Out of those 10 to the 500 possible valleys, Almost all of them are barren, sterile, and hostile to anything resembling life. But then you find one. A tiny, precarious little valley where the cosmological constant, that terrifyingly precise number, this is where the work of Alan Guth and Andre Linde comes in. They gave us the engine for this landscape: eternal inflation. According to Linde, a brilliant, energetic mind who brought his Russian intensity to Stanford, the universe didn't just bang once and stop. Instead, space is constantly foaming, creating bubble universes at a staggering rate. Each bubble rolls down into one of the valleys in the landscape. Our universe is simply one of these bubbles that happen to land in a valley where the physics allows for stars, planets, and curious apes with blackboards. It's not that the universe was designed for us, it's that we can only exist in the 1 in a trillionth pocket where the math doesn't kill us instantly. I called this the anthropic landscape, and it turned the world of physics upside down. We weren't looking at a master clockmaker's design anymore. We were looking at a cosmic accident on a scale so vast it felt like a betrayal of everything we thought physics was supposed to be. Now, you have to understand, this wasn't just a polite academic disagreement over coffee in the Stanford faculty lounge. This was a war, the String Wars, as the press later called it, and it was a battle for the very soul of what we call physics. On one side, you had the old guard, the practitioners of what I call elegant physics, led by titans like David Gross. David is a Nobel Laureate, a man of immense intellect who helped give us the theory of how quarks are held together. To David, and to many of his generation, the goal of physics was clear. It was Einstein's dream. You were looking for that one single, unique, beautiful equation. Maybe something you could fit on a t-shirt that would explain why the universe had to be exactly the way it is. They wanted a theory that would calculate the mass of the electron or the value of the cosmological constant from first principles, leaving no room for chance. When I started talking about the landscape, about 10 to the power of 500 different possibilities, where the laws of physics were just local accidents, it felt like I was throwing a grenade into the middle of their cathedral. David Gross made his feelings very clear at conferences, often standing up and arguing that the landscape was a surrender. He felt that by invoking the anthropic principle, the idea that our universe has these specific properties simply because those are the properties required for us to exist, to observe them, we were giving up on science itself. To the critics, the anthropic principle was a substitute for thought. It was seen as a way of saying, well, it's just a coincidence, so stop looking for the deeper reason. I remember the tension in the air at the Kavli Institute for Theoretical Physics in Santa Barbara. There was this sense that if we accepted the landscape, we were admitting that the universe was messy, statistical, and ultimately unpredictable in the way we had hoped. It was the shift from a universe of uniqueness to a universe of contingency. And then there was Lee Smolin. Lee is a brilliant, deep thinker who approached physics with a kind of philosophical restlessness. He couldn't accept the landscape because he felt it lacked what Karl Popper called falsifiability. If a theory can explain every possible value of vacuum energy because there are 10 to the power of 500 versions of it, Lee proposed an alternative he called cosmological natural selection. He suggested that black holes might be the seeds of new universes, and that universes that produce more black holes and thus more offspring would eventually dominate the multiverse. It was a biological analogy, much like my own, but Lee wanted a mechanism that stayed within the realm. But the most shocking, while Lee and David were fighting from within the tent of string theory, people like Peter Woit were attacking from the outside. In 2006, Woit published Not Even Wrong, a title taken from a famous put-down by Wolfgang Pauli. Woit's argument was even more biting. He claimed that string theory had become so flexible, so capable of morphing to fit any observation via the landscape, that it had become a mathematical house of cards. I took these attacks personally, not because I was offended, but because I felt the critics were missing the point of what the math was telling us. Physics isn't about what we want the universe to be. We might want it to be elegant and unique, like a single perfect diamond. But if the math of D-branes and Calabi-Yau manifolds, the work of people like Joe Polchinski and Raphael Bousso, tells us that there are 10 to the 500 ways to fold the extra dimensions, then we have to deal with that reality. We can't just ignore the results because they make our t-shirts harder to design. This wasn't a surrender, it was a realization. We were moving from the era of the geocentric physics, where our corner of reality was special, to a Copernican physics where we are just one tiny bubble in a vast, foaming sea of possibilities. It was terrifying to them because it took away the comfort of certainty, replacing it with the cold. So, where does this leave us? We started this journey with Einstein's dream, the hope that we could find one single, elegant equation that would explain everything from the skip of a stone to the birth of a galaxy. Einstein famously asked whether God had any choice in creating the world. For nearly a century, theoretical physicists operated under the assumption that the answer was no. They believed that if we just looked deep enough into the heart of the atom, we would find a mathematical necessity that demanded the universe look exactly the way it does. But the landscape, as Leonard Susskind presented it in his 2003 paper, The Anthropic Landscape of String Theory, has shattered that dream. It has replaced the crystalline perfection of a unique theory of everything with a sprawling, messy, and frankly, look, this is a profound pivot in the history of science. It's a shift from physics as a search for the rule to physics as a study of the population. Susskind often uses a biological analogy here that I think is very helpful. Imagine if biology tried to find the one true animal, the single, mathematically perfect organism that must exist by necessity. It would be an absurd goal. There is no perfect animal. There are only animals that are fit for their specific environments. The penguin is a statistical success in the Antarctic, but a failure in the Sahara. In the same way, Susskind argues that our universe isn't a mathematical requirement. It is an adaptation. It is one of the 10 to the power of 500 possible vacuum states that just happens to have a cosmological constant of 10 to the power of minus 122, a value small enough to let us grow and breathe and ask these questions. This legacy has transformed how we think about the future of physics. It led to the string wars, with thinkers like Lee Smolin and Peter Woit, but it also birthed new, rigorous frameworks like the Swampland Initiative led by Kumran Vafa at Harvard. Physicists are now trying to map the borders of the landscape, trying to figure out which of those 10 to the power of 500 universes are actually consistent with the laws of quantum gravity. We've moved from asking, why is the universe this way, to asking, in which parts of the map is life even possible? It's a humbler kind of science, but in many ways, it's more honest. We have to face the fact that we might just be a statistical outlier in a near-infinite sea of we are the lucky ones who find ourselves in a Goldilocks vacuum, a tiny patch of the landscape where the math doesn't immediately tear us apart. That realization is haunting. It means our existence isn't written into the foundational laws of the cosmos. It's a fluke, a winning lottery ticket drawn from a bin of a trillion failures. But maybe there's a strange beauty in that accident. If the universe were a unique mathematical necessity, we would be nothing more than a predictable consequence of an equation. In Susskind's landscape, we are something more fleeting and precious. We are a rare moment of consciousness emerging from a cosmic statistical collision. We are the part of the multiverse that woke up and looked around. The universe is not only stranger than we suppose, it is stranger than we can suppose. If this journey through the mind of a genius left you thinking, subscribe and hit the bell. Tell us in the comments.